Hello and welcome to our video. We are the Interplanetary Propulsion Team R presenting the nuclear thermal propulsion system. In the pursuit of finding a suitable propulsion system for interplanetary travel, we researched the Vasmir and rotating detonation engine, but both were rejected due to marginal increases in efficiency and being largely theoretical. Thus, the NTP was the best option that seemed feasible and provided a dramatic increase in propulsive power and efficiency. The NTP is a propulsion system that uses heat from a nuclear reactor to accelerate a gas propellant to produce thrust. As seen in the diagram, it is a complex system that requires materials that can withstand nuclear reactions. Werner von Braun developed the idea back in the 1960s, and various experiments have shown that it could provide higher thrust levels with much greater efficiency. Hopefully, in the near future, nuclear thermal propulsion can become a usable option for interplanetary travel.
For mission requirements, the first consideration in this mission is the stakeholders. This is a scientific mission that will most likely be headed up by NASA, who has a vested interest in space exploration. Additionally, American taxpayers are stakeholders because they fund NASA. Both NASA and American taxpayers want the mission to be low risk, safe, cost effective, and produce valuable data. NASA needs a system that can travel to the Jovian system in a safe and cost-effective manner. They also need a system to transport sensors and other data devices to record as much as possible once near Jupiter. Other scientists also have a vested interest in NASA's success, as information collected during a mission could inform mass amounts of research in future missions. Finally, each stakeholder needs data to be collected about nuclear thermal propulsion systems performance itself to determine its efficacy and its effective tool to use for future missions.
The payload was sized by extrapolating each of the major subsystems from prior deep space missions to increase the capabilities and robustness of the intense radiation of Jupiter's magnetic field. For example, the primary goal of the orbiter is detailed surface surveys of each of the Galilean moons, and so the HiRISE instrument on Mars Reconnaissance Orbiter was used as a basis, and extra mass was added to account for increased radiation shielding. Similar processes were carried out with communications and electronics, which were also based on the Juno probe, and power, which uses a set of general-purpose heat source radioisotope thermoelectric generators, similar to those used on Galileo, Ulysses, Cassini, and New Horizons. To determine the delta V required to orbit all 4 Galilean moons at an altitude of 300 kilometers, a patch count analysis was carried out, and the delta V was computed to be approximately 7 kilometers per second, and an extra half kilometer per second was added for course corrections and to account for inaccuracies in the patch count analysis. Similarly, the delta V needed for the transfer stage was computed using another patch count analysis to be approximately 6.3 kilometers per second for the Earth departure burn, 4.6 kilometers per second for the Jupiter arrival burn, for a total of 10.9 kilometers per second of delta V.
Nuclear thermal propulsion has 3 different cycles. Hot bleed and cold bleed both have bleed flow after initial propellant expansion that routes through the turbine to drive the pump. Hot bleed also includes exhaust products, while cold bleed does not. This gives hot bleed higher cycle efficiency, but leads to more thermal stresses, while cold bleed has a much more reliable and simpler turbo pump system. The expander cycle is a cycle already used in rocket engines today, though never with NTP. Expander cycle has no bleed flow. Instead, after the propellant is expanded, it goes through the turbine and then the reactor chamber. NASA Glenn Research Center has estimated the specific impulse of these cycles at 900 seconds with a wet to dry mass ratio of about 3.2. For our inert mass estimate, we based a conservative estimate on the Falcon 9 inert mass, allowing for the nuclear reactor that drives propulsion. With inert mass at 58 metric tons and the scientific payload estimate being at 22 tons, we then use the rocket equation as well as our total delta V of 10.9 kilometers per second to calculate our propellant mass at around 191,000 kilograms. The total mass is then 271,800 kilograms, with a mass ratio between 3.3 and 3.4, slightly larger than the estimate obtained from NASA Glenn.
There are heavy risks associated with using nuclear power at any time, but even more so in outer space. If the rocket blows up before exiting Earth's atmosphere, it's as if a nuclear reactor blew up over populated areas. To avoid such a catastrophe, the United Nations has written 5 treaties with guidelines and laws on what can and cannot be done with nuclear power in space. This is to avoid disastrous effects on human life and our planet. Before such legislation, the Soviet Union had a satellite with nuclear material explode. Back in 1978, the Cosmos 954 was carrying 45 kilograms of uranium that exploded upon an unplanned reentry over Canada. This resulted in over 100,000 square kilometers of land to be affected by radiation, resulting in massive ramifications. Despite these risks, there hopefully will be continued research into powering interplanetary travel with nuclear thermal propulsion systems as more rules and regulations have been created to prevent such incidents.
In closing, the NTP is a viable option for efficient space travel. As outlined in our research and calculations, a system powered by an NTP is vastly more powerful than any other propulsive system out there. Further research and development of the nuclear thermal propulsion will produce a highly efficient form of propulsion that can be applied to missions like ours. Thank you.